Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool Cloud, and today we're going to talk about how you can calculate the required borehole depth. So although this method is implemented into GHEtool and it's rather straightforward to use, we're going to spend this video talking about different methodologies which are described in literature on how you can calculate the required depth. And in another video, we will be looking at how you can do it in practice using GHEtool Cloud. So you can see this video as the background information you need in order to understand this method and also its shortcomings, or at least its assumptions. So let's get started. So in concept, calculating the required depth is rather straightforward. What you do is you start with a certain design, certain borefield configuration, a certain depth, and you calculate the temperature profile, and then you're going to check whether or not your average fluid temperature stays within certain temperature boundaries. If they do, well, your field is correctly sized, and if they cross these limits, you're going to increase the depth, you're going to drill a little bit deeper, you iterate the process, you recalculate the temperature profile, and you keep doing this until you converge with a temperature profile that sticks or that stays between those temperature limits. So this is how you can do this conceptually, but of course there are different ways or different accuracies on how you can do this. And in literature, based on the work of Ahmad Vacht in 2018, there are 5 different levels of accuracies, ranging from an L0 method, a rule of thumb, to an L4 method with an hourly resolution. And in this video, we're going to spend some time talking about all those different methods, what are their advantages, their shortcomings, and we will also spend most of our time talking about the L3 and L4 methods, which are implemented in GHEtool and which you can use in your own projects. So if we start with the level 1, the L0 method, these are your typical rule of thumbs in the form of X watt per meter. So if you have, your peak power of your building, then you know directly what your total borehole length should be, because you assume in this sizing method that your borehole length, total borehole length, is directionally proportional to your peak power. But of course, this is extremely inaccurate because it does not take into account your configuration. If you're in a dense configuration or your boreholes on a line, they do not take into account your depth, your ground temperature, or your ground properties for that matter. It does not take into account your imbalance, whether you're extraction or injection dominated. It does not take into account your peak powers, your borehole thermal resistance. So, as you can see, this method should be avoided when sizing bore fields due to its high inaccuracy. And if I'm not mistaken, our first article over on our knowledge base talks about the importance of borefield design software and also the inaccuracy of these methods, with typically an over or under sizing with a factor 2 to 4. So it should be avoided. The other methods, they do take into account the configuration, and we start with the L1 method. What we there do is that we assume a constant load. So what we do is we take the yearly demand for heating and cooling, or for injection and extraction. We average it out into a constant load. So we assume that we apply a constant load for a whole simulation period on the ground, and then we can take into account, using concepts like the G function, which we talked about earlier, the configuration, the borehole to borehole interaction. We can take into account your borehole depth because it influences the G function. We directly take into account the imbalance because the imbalance leads to the constant load, so it's directly related to that. We take into account our borehole thermal resistance. So this is already way more accurate. The problem with this method is that we ignore the first year of operation because we look at the long term with our constant load. We ignore monthly variation as well. So if we would visualize this method, we will end up with a temperature profile like this, where you can indeed see that we just have a constant heat extraction in this case. Our borefield cools down year after year, and we are sized based on the minimum temperature in the 20th year. So for those who remember our video about the G functions and the long-term effect, this is exactly the profile or the G function for this particular borefield with this particular depth. So level 1 and level 2, or level 0 and level 1 are rather straightforward. But for the other methods, we're getting a little bit more accurate. And before we dive into them, let's jump back a little bit of bringing again on your attention the borefield quadrants. Now, if you have not watched our video related to this subject, it's linked in the video description below. But what we said here is that no matter the borefields, they will always be able to be categorized in one of these 4 quadrants. So each borefield should or will be sized or limited by either the maximum or the minimum average fluid temperature, and either in the first or in the last year of operation. So when we're thinking about how you should design your borefield, you do not know a priori in which of these 4 quadrants each borefield will be. So what you do is you take your borefield and you size it once in quadrant 1, in 2, in 3, and in 4. So we size it based on the maximum temperature in the first year, maximum in the last year, etc. And then we take the maximum size of all these 4 sizings, and that will be our borefield size. But for those of you that wondered before, and perhaps also now, why there are 2 different colors, 1 and 4 and 2 and 3 are in different colors. This is because we discovered that it's not needed to size each borefield in all of the 4 categories. Because imagine that we have the borefield in quadrant 1, and we say, well, let's size it in the last year of operation for the maximum temperature. So then this peak will be at 16 degrees in this case. It will be sized in quadrant 2, but of course the temperature before that, due to the imbalance, will be slightly above the 60, and the year before even higher, etc. So if we would size this borefield, we'll end up immediately with a borefield that should be sized here due to the imbalance. And the same is true for quadrant 4. If we would have sized it in quadrant 3, due to the imbalance, the second year will be lower in temperature and should be the critical year, etc. So when looking at the imbalance, you should either size it based on quadrant 1 or 4, or in quadrant 2 or 3. So you only need to check 2 of the 4 quadrants because you know a priori which is your imbalance. So if we paraphrase this, whenever we're sizing a method with our borefield with methods L2, L3 or L4, you size it for the maximum average fluid temperature, you size it for the minimum average fluid temperature, and then you take the maximum size of both in order to find the borefield which has the bigger size. So if we then take a look at level 2. So level 2 uses 3 pulses per simulation period instead of 1. So our level 1 method can be said to be a 1 pulse method because we only assume there is 1 continuous heat load. Here we assume there are 3 pulses. So we again have our imbalance pulse, which is basically our level 1 pulse. It's constant in time. And then we also take into account our peak power, our peak pulse. And we discussed earlier in the previous video the short-term effects of your borefield, and we said that the peak power is indeed really important. So we take into account this peak power explicitly in this method. But also, and that's the third pulse, the monthly energy exchange in the month in which the peak power occurs. So imagine that in the case of extraction of heat from the ground, this typically occurs in winter. for example in January, this month in which this highest peak power occurs is typically also the month in which the highest energy extraction occurs. So both the peak power and also the monthly energy exchange is important. And this we take into account with this method. The L2 sizing is implemented into GHEtool, but not in the cloud version. And this is because when we compare it to the more accurate model, which we will discuss in a minute, it's a little bit slower, but it also lacks in accuracy. So it's useful for cases in which you need 100,000 of simulations, because then it makes a difference computationally. So it takes also into account the configuration, borehole depth, the imbalance, and the borehole thermal resistance. But it ignores again the monthly variation, because we take only into account a monthly and one peak pulse. Now it's not that easy to visualize this method, but if you would do so, it looks a little bit like this, where you indeed see the same constant load as before with your level 1 method. Then you see here in the last year one sudden decrease, which is due to the monthly peak, and then we have on top of that our peak power as well. So this is a little bit how this method would work if you would visualize it. But now let's move to the methods which are actually implemented into GHEtool, which is the level 3 method, which is the most accurate method when you have limited information. So what it does is it moves away from 3 pulses for the whole simulation period towards 12 pulses per year. So we take into account every month for this method. It's implemented into GHEtool Cloud. It takes the same things into account, imbalance, configuration, etc., but also now the monthly variation, which is important because depending on your building type or your insulation degree, etc., this has an effect on your sizing. The more spread out your energy exchanges, the more accurate this method will be. One disadvantage of this method is that we still need to assume a peak duration, a duration of our peak power, because we're working on a monthly time scale. We do not know exactly how long the peak power lasts, so we need to make an assumption for that. Typically it's between the 6 and 12 hours, and if we calculate it, we get to the temperature profiles you're all familiar with. We've discussed about them time and time again, where you see the monthly variation indeed, and again we're sized here in the last year of operation. So this is typically how you size a borefield. Now we are able to go a little bit further and even more accurate with the level 4 method, which is the most accurate method. It uses an hourly time step. This is also implemented in the cloud version. And the main advantage is, since we're now using hourly data, we can not only take into account the monthly variation, but also the hourly variation. So we go to shorter time scales, and we also now can make abstraction of the peak duration, because when we have the hourly data, we know exactly how long the peak power occurs. So that's why this is the most accurate model. But even so, it can be enhanced, because we do not take into account yet the borehole dynamics. So if you recall our discussion on the short-term effects, where we talked about the borehole thermal resistance, if you do not recall that, it's linked in the description, but we said there that it's a steady state model. So we assume that all the energy exchange is immediately coming from the ground, and the thermal inertia of our fluids and our drought is not taken into account explicitly. We're now working together with the University of Leuven to come up with newer models to actually take this into account and to make the level 4 even more accurate than it is today. And just to complete our story, if we use GHEtool with the level 4 method, we end up with a temperature profile like this, for example, where we now have, as you can see, a way higher frequency. We now have way more, or a higher data resolution, let's say. But we're now also again sized in the last year of operation for this case. So I hope you found this video interesting, talking a little bit about the different sizing methodologies. The next video will be way more hands-on, where we go into GHEtool Cloud, see how you can use this method. And we'll also be talking about an error that can occur rather frequently, about being unable to solve your the required depth due to the geothermal gradient. So if you have seen this error before, please subscribe to this channel so you get notified when this new video comes out. And if you find this video interesting, consider subscribing, sharing it with your colleagues as well. And I hope I see you in the next video. Take care. Bye.